data, and when you're doing the analysis of it, you need to determine what the uncertainty is in your value, right? Does that make sense? So you got a value, so just remembering, because it's been a couple days since we did this. Ballistic pendulum, so you had the ball bearing, you launched it, it hit that little ring, and then that ring swung up, right? And you found the velocity based on the height that it went, right? Does that make sense? Does that match with what we did? Yes? Okay. And from that, you were able to calculate a velocity that was on the order of like 5 or 6-ish. Does that sound about right? So you have like 6-something meters per second. And that's a lovely thing to be able to say. I know that the velocity of this ball bearing is moving at 6 meters per second. Like, that's cool. But how well do you really know it? That's what I want you to figure out. Okay? That's what this extra part of it was. Because everything that we measure has uncertainty, and I want to know what that uncertainty value was. Okay? So if you haven't done it yet, and we'll do another lab like this in a little bit where you'll have to do this uncertainty thing again. So I just want this to kind of stay in your brain. When you had the expression, it was something like, wasn't it like M1 plus M2 times the square root of 2GH over M1, something like that? Does that look right? So what things did you measure in that expression? We measured M1, and we measured M2, and anything else? The height. So you should be able to tell what your uncertainty, just your reading error, straight up reading error is from each of those things. How do you tell a reading error in a measured mass? Half of the smallest division. So if you look carefully on the triple beam balances, it breaks it down to, I think, the tenth of a gram, correct? So then that means that the reading error, or the uncertainty in M, is how much? 0.05 grams, right? So we could convert that to a certain number of kilograms by moving the decimal over 3 more times. Does that make sense? So that's going to be like something on the order of 5 times 10 to the, I'm doing this right, negative 5th. Do you guys agree with that? Is that okay? Awesome. What's up, Caleb? Sorry. So that's your reading error in M. So you need to figure out what your percent error is in each of those measured values. How do you do that? How do you find percent error? Right. So your percent uncertainty in M1 is going to be delta M divided by M1, right? And then multiply it by 100. And that'll give you your percent uncertainty. And so then you have a percent uncertainty in M1, a percent uncertainty in the sum of the M's, and then a percent uncertainty in H. And then what do you have to do here? You have to put, how do you deal with those percent uncertainties to find an overall percent uncertainty? Do you remember? This was like day 3 that we were together. It was a while ago. Why don't you open up your notes? Look it up. I know it was there because you did it. I know it was.
Find what that is.
So the rules, yeah.
Add
what? Always? When you multiply and divide, right? So do you guys all agree with that? Do you remember that? If you don't remember that, you need to look back at your notes. Absolutely. So you're going to do the percent uncertainty in M1 plus the percent uncertainty in M1 plus
last time, we're going to use
M2
chain rule to break that up.
plus,
So
is it the percent uncertainty in H?
I'm going to say negative K times S minus S
Why 1/2?
is equal to M times
Right, so you're
dV
gonna multiply
dx
by the exponent.
times ds.
Oops, percent uncertainty.
But you say, hey, wait, ds dt is just
Does that make
velocity
sense?
again. It's like we've seen
That
this
gives
before.
you an
or
overall
something.
percent uncertainty. So is that what you write right here where it's plus or minus?
Friends that are watching this later. M times velocity.
I see people staring at me, a few heads moving, I'm not sure.
Over now. Pretty obvious.
Yeah, you have to use the 6 again, right? So percent uncertainty
And oh my gosh,
means
it's like we're ready to integrate again.
delta,
Same
we'll call it
kind of
delta
idea
V
that
over
did before.
V, right? So you want to know what delta V is.
With respect to
Does that make sense? You want to know what delta V is, so you need to multiply the percent uncertainty by V.
Sometimes the derivation is trying to get us to a certain spot.
Complicated,
And
but it is important to do it this way. It's important to set it up this way so that you've got all of the pieces and so that you have an accurate measure. Okay? Do you have any questions about that?
One.
I feel like some of you are looking at each other like, oh, maybe I shouldn't have turned it in yet. Is that true? Yeah? Okay. So let me make a deal with you. I would like to move on and do some other things right now. And then I'll get those out, and if we have some time at the end, we can look at them, and I'll give them back to you for sure. Does that sound okay? Okay. So let me tell you what my plan is for the rest of the day. But I want to make sure, well, before I move on, does that make sense to you, that process? So you know what you need to do. Okay, good. So my other plans for today, I want to do a little physics, like actually do some physics, talk about conservation of energy a little bit more because we get it, but there's more to it. And then I have tests to go over with you also, and to talk about grades and stuff like that. Does that sound okay? Okay. So I'm going to get a new piece of paper. You may want to get a new piece of paper too. And you're not going to let me forget to give you back those things if you want them back.
That way, we're going to integrate using.
Okay, new topic. I just didn't want to forget to do that today. So I hope that this isn't too crazy in your brain.
Okay. We're comfortable with it? You sure? Yeah. Well,
do you remember a couple times ago?
It was much easier.
I was telling you how much I disliked energy bar charts. Do you remember that? Like I was kind of going on a rant, like I think energy bar charts are stupid. Well, I kind of changed my mind this morning. I'm not saying they're like the best thing in the world, but I kind of appreciate them a little bit more today. I don't know. Maybe I just woke up on a different side of the bed or something. I don't really know. But we're going to do them a little more today because I think that it will be good for us. So, here we go. Frog, yes,
that's what we're finding. Okay, the SE again is just a constant. And the limits of energy are just the final velocity.
Wild and crazy ride, right? Like we didn't even have that yet. What I'd like you to do right now is to draw 3 energy bar charts.
Is that okay?
When he's up at the top.
Okay, so
let's. When he's falling somewhere in the middle, I don't really care.
I'm gonna leave the right hand side
and then
for
one
because
when he gets to the bottom. Before the ground
So,
has stopped him, but
because I know that it's going to give me a nice solution.
does that make sense?
And it's equivalent to what I was talking about, but it's convenient for me.
Go ahead and do that.
U is equal to x minus e. If that's the case, then du is equal to what? SE is a constant, yes. It's just a number. What's that? Just 1, right? So it's just going to be 1 times ds, right? Is that okay? And so then we can rewrite our integral. Oh, and then also.
All right. If you were going to teach someone how to draw an energy bar chart, what's one thing you would tell them they need to make sure to do, to keep track of? Yeah.
So that's really the displacement.
The same amount of bars. What do you mean by that?
SI is like the initial position. But if I'm
okay. So like I'm going to have 1 bar here and 1 bar here.
So I've got SF. It's going to be SF.
I think you're there. I think we need a couple more words.
That's going to be some final displacement. So using this stuff, I can rewrite that integral to say the integral of, so it's going to be delta SI.
Oh, with the boxes. Is that what you're talking about, David? Okay. Okay. So you need to set it up into boxes, and you need to make sure that you have the same number of boxes in each
what does that
chart.
become?
Does that make sense? Okay. Does it matter how many boxes we choose? No, it's arbitrary.
Hold on.
Okay, that's one thing. So we need to make sure the same number of boxes. What else do we need to do to set up an energy bar chart?
What's?
So So if I have this, look at me.
What's
I'm so
that?
cool. What else am I gonna?
Oh,
What else do I need to know?
Yeah, just pull that out.
Did I
What's that?
I don't think so. I don't think that's
Label kinetic and potential energy, right?
over.
What kind of potential energy do we have?
I'm gonna apply,
Gravitational potential, and we have kinetic.
so delta S.
Do we have any other kinds of energy in this story?
So that's going to give us
What if we did?
Negative
What would we do?
5.
No, crying is the wrong answer there. At the top, how much gravitational potential energy does it have? What'd you say, V?
Minus negative K delta S I squared.
4 bars.
Okay.
Okay. 100 is a lot. No. I don't want to. You can on yours, but I'm not going to. Okay. Does anybody have other things besides 4 or 100? Like apparently Isabel
All right,
has
on the other
drawn on
side.
her
Because there was
paper.
another side to that. Darn it.
Any other numbers that you've chosen?
But it's an easier side because we've already done this one.
Number of boxes wise. What'd you have? You had 3.
And
Anybody
this
else?
side
Maybe
over
a
here,
0?
if we remember from our time together
Would that be
before when we
wrong?
were doing derivations, it's going to give us our statement.
Would it?
of kinetic energy, right? So something v final squared minus 1/2
What, Chris?
v initial squared.
So would it be wrong? No. Can I do that? Can I put 0 by h equals 0 up
Say
here
that
where I'm
again.
going to drop my frog from? Of course
Yes,
I
the
can.
other half of it.
So I could
Yeah,
start
that's
off with
asking.
0
The right-hand side
energy.
is-
0
is
total
easy.
energy. Is that allowed?
Yeah.
Sure. So how much energy
So
would I have here?
what we get out of this whole
How much
deal
would I have here?
is another statement of
0.
equality
Right? Does this make sense?
that, well, the right-hand
Yes.
side
Please make sure that you're listening. I feel like we're kind of zoo, and I need you to be here so we can go faster, please. Thank you. What about in the middle? Gravitational potential energy and kinetic energy. What do you know about them now if we use this one as the starting point? They're what? Yeah, kind of in the middle. Yeah. What does that mean? So use more words. Be more specific.
like 1/2 K
Okay. So you've got like maybe 2 boxes of potential
delta X.
and 3 boxes of kinetic. Is that right?
I'm gonna well.
What's wrong? Same and same, right? So I'm going to do 3 there, then I'm going to do just 1 over here, right?
What is this?
Is that wrong?
It is.
No, it's okay. I didn't tell you where in the middle, but at some place in the middle, the potential energy is going to go down by a factor, right? Like this.
That was a lovely little conversation that just happened.
What
back
about at
there.
the floor?
Wait, you read the book or something?
What about at the floor? What does the floor one look like?
Oh, yeah. So just energy.
Does there have to be no potential energy? Seth, why do you say no?
This energy has this expression here.
Okay. So I could have
Okay.
my h equals 0 down in Mrs. Cross's room, right? Sure I could. And then if it
Okay.
falls and hits the ground,
Delta
then does it still have potential energy
squared
gravitational?
plus 1/2.
Sure it does. So we have to be
and
careful
v
about saying yes or no, it's
squared
wrong.
equals
But according to the way that
1/2
we kind of set it up, it's going to
delta
look
F
something like this. And how many boxes are going to be
squared
here?
Plus 1/2.
Life is
and
good?
V finals.
Okay. Energy is conserved.
So
Everybody's
if
happy.
those are the only 2 kinds of energy that are
Okay, now hold on.
The total
Here's the situation. I want you to watch carefully. There's the frog.
equals the total energy.
Energy is conserved, right? Okay. So here there are going to be 5 different places that I want you to look at. So before we even go anywhere, erase your boards. I want you to draw 5 energy bar charts. You're going to have 5 axes. If you want to do it in 2 levels, that's fine with me. But 5 energy bar charts.
When we're talking about
Please
this-
do not waste my markers. I've had to throw a bunch of markers away already this year, and I have to buy
You
them
could, but
myself.
then you wouldn't have
So
a statement
don't waste them, because once they're
But
gone,
the quantity,
I may not buy more.
for
Okay? So 5 energy bar charts.
About another country.
Once you're ready, put the cap on your marker.
Questions
put your
about
marker
that?
on Here so I know that you're ready.
The last little piece that I wanted to add in here, because I almost forgot, was when you're writing elastic potential energy, potential energy is marked with a U. Remember we talked about the last time that gravitational is U sub G. This is going to be U sub S. We don't want to write U sub E, even though we like it because it's elastic. because U sub E is electric potential energy, and we'll get there, but we're not there until after winter break.
Okay. This is number 1.
I know, right? Like, whoa, we have a
legitimate two.
So here's number 1.
the beautiful thing.
Here's number 2.
Okay.
3, number 4, number 5.
So as I have to, because it's my job, I have to articulate to you that I am not at all condoning any sort of violence or use of guns or any of that. That's my statement.
You can talk to each other,
But
that's
if you've
fine.
ever seen
But I want you to think
little
about it
Dart
together.
gun, they're kind of fun. And it's cool because they do store elastic potential energy, right? Just like I mean, that's how it did it. It's the same deal.
Good progress. Some of you are kind of mad, and I want to help you so that we're not feeling so. Okay, so let's start by deciding on an H equals 0. Does that sound okay? So that we're all talking about the same thing.
It's compressed.
Does anybody have a suggestion? Where do you want H to be?
Centimeter. Don't forget
At the floor. Okay, so I'm going to write that down just so that we don't forget. So H equals 0 at the floor.
What speed does the dart acquire?
Okay. Now,
Go.
talk to me.
What's up?
Talk to me about what you wrote down, what you were struggling with. What were you and your table mates thinking about?
Okay.
You can tell me there are 5 graphs to draw. So tell me about one of them.
Silly squares. So we're happy?
Yeah.
Okay.
It's
Okay,
to
sweet.
be wrong. It's okay to
Next.
go out on a limb.
I kind of like this one because it makes you think a little bit. All right. We have a ball with a mass starting from rest. The vertical distance 55 centimeters.
Okay. So what kind of potential energy are you talking about? Gravitational potential energy is defined by what expression? MGH? Okay, so if it's defined by MGH, and you're telling me that the H is equal to 0 at the floor, then what?
It starts out. This is 55 centimeters.
What were you going to say?
And then this is.
Mm-hmm.
You start me out, and then I'll
Okay.
talk to you.
In 1, it's not moving, so there's no kinetic. There's no gravitational potential because it's at the floor.
Okay.
Then in 2, it has obviously potential energy.
Do you want to talk to us, or you? You
Okay.
can do whatever you want.
So, like, these graphs don't show, like, all of the energy in there. So, like, you were exerting energy to move it, so
What kind of energy?
in the motion
What kind of
from it being in the floor and
Grav-
pushing it up,
Right.
you were exerting energy on it, so the energy was conserved to give it that gravitational potential.
potential?
So, like, if it,
No.
for
At
constant
B,
to work, then it has to show the energy of
let's make this
everything in
3.
the system, like including
What kind
you
of B?
and
Yep, right here.
What do you guys think of that?
So yeah.
Does that seem to kind of make sense to jive with you? Yeah. So the whole point of this is exactly right. The whole point of this is to figure out what we're considering a system. And that's a really, really big
Is
question.
it all?
What is in the system? In the first example that we did, what were we considering the system to be?
1. Does that make sense?
What was in the system?
Some negative.
The frog. The frog, yeah. Is it okay for the frog to be the only thing in the system?
Yeah.
Sure, you can pick anything. The cool thing about this energy stuff is you get to pick everything, right? You get to pick where H equals 0. You get to pick what's in the system. Like, you are in control, right? This is a big deal. But, as Jordan said, so I'm going to put something in between these two graphs. I'm going to put a circle in here, okay? And that circle represents the system. If I have no energy going on here, and I have some here, is energy conserved in this story right here as I have pictured? Does 0 equal 4? No, so is energy conserved?
All of the potential energy gravity.
Come on, friends. Say it out loud.
Would have.
No! Believe it! Is energy conserved? It's Friday afternoon. You're not that tired. I'm going to ask it one more time. Humor me. Is energy conserved? No! The answer is no, it's not. River, wake up, my buddy. We need to get this figured out. Jeez. I'm trying to teach, all right? Jeez. River wants you to know. Yeah, they just come to see me after they see you. They were all mad. Was that what you guys were mad about? Were you mad at Marchetti? Oh! I'm going to pause this for our friends that aren't here. Sorry. Energy is not conserved. We just said that again. So, this is all kinetic. So, we've got, what, 4 bars of kinetic or something like that? And then we're going to have this little circle thing here. Again, that's the frog. And what's happening this time? Yeah, there's energy that's leaving the system. Where's that energy going? Into the floor. It's true. Does that kind of make sense? Is that okay? So what we just proved here is that energy is not conserved. Well, that's a frustrating situation because all of physics and all of the universe is based on the theory that energy is conserved. Dang it, so we just broke physics. Guess we're done. Except we're not, because Jordan did save us earlier by saying that we can just define our system bigger, right? Yeah. So in what system is energy actually conserved? What do we have to include in our system? Me and what else? And the frog and the floor, right? So let's do that just for kicks. Here we go. So we're going to do the same story. So you can erase your bar charts, but maybe leave the axes, except he's like, wait, I just started erasing. Well, you can add those axes back in. I want you to draw bar charts if the system includes me and the frog and the floor / air, I'm going to say. 5 bar charts again. 5 bar charts again. I want to know what they're going to include. Okay. Maybe you're going to have more than just 2 things on your x-axis. I don't even know what to call you.
I want to go back.
Talk to your partner. See if you can come up with an idea. What are you going to do to make this a more complete story?
Said that energy was conserved.
Toast. Peanut butter toast energy. Yeah. Yeah. So when it's on the floor, we have all kinds of energy. We have gravitational potential, as we know. We have kinetic, and then you added some other ones with all kinds of awesome names. But if we're going to be official about it, it's a type of potential energy, right? It's peanut butter toast potential energy. If we were going to be a little more formal than that, we'd probably call that what kind of energy? What kind of potential energy? Chemical potential energy, yes. That's chemical potential energy, okay? You consume things, your body converts that stuff into the energy that allows you to do stuff. And so that's going to be where all of our energy lives at the beginning. And then we know what these guys look like, right? The held high and the da-da-da-da-da. So I convert 4 boxes of chemical potential energy into the gravitational potential energy that is what the frog has. Does that make sense? And then the frog falls, as he always does. And then what happens right here between the floor and when it stops? What happens?
Not the period amplitude. I got lots of words there. No. And we'll prove that later, but...
Yeah, it's giving it off, right? So it has kinetic energy, it hits the ground, and if you think about it, it's all kind of squishing around and moving around and stuff like that. And that is causing something to be given off. Some of it's sound. A lot of it is actually kind of the same thing as friction. It's heat energy, thermal energy.
If energy is conserved...
Yeah, it's thermal energy that's coming out. So I would also include some sort of, we'll call it heat here, and there's no heat there, but I would put all of that 4 bars of energy in there. Now, there's a lab that I do with,
Is it just going to stay at equilibrium?
that I will do with the AP Physics 2 people next year
It's
when we
gonna
do
go up,
thermo,
it's
but
gonna go up and down, right?
actually, hold on, let me go get it and I'll show you it because it's kind of cool. That's all exciting, but it's got, shot it. Okay, a little
Well,
piece.
right, so, okay, hold on, so what now?
And I put a little hole in one of the ends, and
Right,
the
so energy has
lab
to go
involves
somewhere.
this.
Right? So some of that has to do with air. But even, let's say that I did
Over and over and over
like
100 times.
do it,
Okay. Very exciting. It's actually lovely. It's kind of, you know, it's kind of like Zen after a while. It's like, oh. Right? So what's happening here? Chemical energy, right? My peanut butter toast is turning into gravitational potential, kinetic, and sound and thermal energy.
happened to it.
And what we do with it is that we take the temperature of the ball bearings before, and we take the temperature of the ball bearings after. And you can tell how much energy they have, right? Because I'm lifting them up, gravitational. So I can calculate how much gravitational potential energy there is. And then the gravitational potential energy turns into kinetic, and that kinetic turns into thermal. And it's actually a measurable difference in temperature
When we're
from the
talking about
beginning to the end. What's that?
system.
Well, that's what I've done over time, right? Because if you do it just once, you have to have a really good thermometer, right? With a very, very small, or lots of symmetry, if you will. But if you have you do it a bunch of times, and yeah, I mean, it goes up by a few degrees, which is kind of surprising, isn't it? But that's what's going on. Okay, life is okay here? Does this make sense to everybody? Okay, so the game is, just like we said with setting h equal to 0, you can set your system to be whatever you want it to be.
The energy will turn.
Sometimes it's more convenient to talk about all of these things like the floor and the person and whatever. Sometimes it's less convenient to talk about that. You want the system to just be one thing. And if you want the system to just be one thing, then you have to acknowledge that sometimes energy is added
Because otherwise, any friction that
or removed
that energy is just going to go out and then either
from the system.
or you have to increase.
There is one system from which no energy can be added or removed. That system would be the universe, right? You can't get any bigger than the universe. Because even if we're just talking about the frog and me and the floor, well, then there's the
But I
air,
love it.
right? And the air's impacting
think you
the
will
outside.
too.
Like it's a ripple effect out and out now. But if you talk about the energy of the universe,
So we
it
have
has
rock,
to be
paper,
the same
scissors going
all the time
on.
forever.
There's
From
people
the Big Bang
fighting,
to
but
now, same amount of energy.
here's the problem that we just worked
Not
on
same amount of order
with
and
the
disorder,
answers in it.
but
So you
same
can
amount
take a
of
look
energy.
at that
Okay?
with the box going down.
How do we change
the
the amount of
loop.
energy in this story? Just to
Then
kind of
over to
regroup
D.
and get this around in our
That
heads.
box then goes through a
I
hollow
was able,
frictionless
so
tube
carboling
out at E across a rough surface, which is why I had to talk
Added
about
energy
friction for a minute. F, and then it hits the
the
ideal
frog.
spring, so no heat's going to be lost to the spring.
to the
So
system.
let me go up and show you the questions again, so you can work on
If we call the
those
system just
at
the
your
frog.
leisure.
What kind of energy did I add?
There you go. It's been fun, friends.
Potential, gravitational potential, right? How did I do that? What did I do? I lifted it. Let's be a little bit more specific. What did I do? Let's talk about it in physics terms. I grabbed it and I what? I changed the height. How did I do that? I had to, like it was sitting there, right? It was sitting there. It's just hanging out. In order for me to get it from there to there, I have to definitely displace it. And in order to do that, what do I need to do to it? I need to apply a force. Okay? I have to apply a force to get it up here. Does that make sense? So I had to apply a force. It is. Okay? A force had to be applied over a distance. That is called, what was it? Work. So work, which is marked with a W, is equal to the change in energy of a system. So by doing work, I'm changing the amount of energy in the system. Okay? I'm applying a force over a distance. Let's talk about another situation. If the system is just the frog, what else changed the amount of energy of the system? What else changed the amount of energy of the system? Let's look back at the picture. What else changed the amount of energy of the system? The floor, right? How did the floor do that? What did it do? Let's talk about it in terms of physics. What did it do? It applied a force. Don't you agree? If the floor wasn't there, the frog would just keep falling. But the frog applied a force. Yes? I'm going to say over a distance. Does that make any sense? Watch the frog fall. He lands like this, and then what happens? So there's a little bit of a distance that's happening there, right? Okay? So the floor is, what do I want to say? Decreasing the energy of the system. And the system, again, here is the frog. So the key here, friends, is that you have to make sure that you define the system. Okay? In this case, the work was changing the kinetic energy. Okay? The work changes the amount of energy in the system by applying a force over a distance. We doing okay? Is this making sense? Okay. I want to think about it in terms of a couple of problems here. Oops. I think I want to do this one first. Let's see. I don't know if you can read this very well because it's kind of a funny picture, but let me make it a little bit bigger and then I'll read it to you so you can certainly understand what's going on. So it says the velocity of a tugboat, so tugboats instead of frogs, but you know, same kind of deal. It increases from 2 meters per second to 4 meters per second in the same direction while a force is applied to the tugboat for 20 seconds. Does that make sense? So we can look at this, friends. This is like a kind of a weird thing. If you have a force applied for a certain amount of time, it's also changing the what of the system? Say it loud.
Momentum.
Momentum! Yeah, it's changing the momentum too. So this is weird. We're changing the momentum. We're changing the energy at the same time. Oh, they're like related. Whoa! All right. This thing says complete the work energy bar chart. So they're throwing work into it now because the system is just what? What's in the system? Just the tugboat. So the tugboat is the only thing in the system. Okay? This one wants the bar heights to be proportional so that this matches. I want you to talk to your neighbors about how you might do this and go ahead and write it on your boards. Okay? Let me make this a little bit bigger. Have a conversation. See if you can figure. Can I pose a question to you? May I pose a question to you? Is the kinetic energy going to double? Jordan's adamant. She gets cranky today, we know, so let's watch out. Yeah, why do you say no? I mean that in the nicest possible way. Uh-huh.
And we know what V is for that. So we figured out what the mass was, and it just does mass of 1. But then your kinetic energy has to be equal to, for the final one, has to be equal to 1/2 of the velocity squared. And since the velocity is 4, then the kinetic energy has to be equal to 8.
Does that make sense? People at her table are like, yeah. Sure. What are the other tables you guys think? Chris, what do you think?
That makes sense.
Yeah? Will, what do you think?
I think it makes sense, but I guess so.
Okay. Well, let's make sure it makes sense for real. Does this statement make sense to you all? There are 2 bars, and that equals 1/2 m times 2 squared. I want to know how many bars are equal to 1/2 m times 4 squared. This is, oops, let me do this in the right color. So this is 1/2 m times 4. Does that make sense? This one is 1/2 m times what? 16, which is really like 1/2 m times 4 times what? 4, is that okay?
Yeah.
So this one needs to be how many times higher than this one? 4 times higher. 4 times 2 is 8. So there you go. We need 8. We need 8 bars. So that's 1, 2, 3, 4, 5, 6, 7. I think that's 8 there. Which means what needs to go? 2, 3, 4, 5, 6, 7. Okay, did 8. How much work is done then? 6 bars. 1, 2, 3, 4, 5, 6. Is that okay? Okay. I'm going to put one more up there. There's actually a part B to this question. I want you to work on part B by yourself first. I'll give you a minute or so to think about it, and then I'll let you talk. But I want you to try it out first by yourself. Here it comes. It's a similar looking question. It says the velocity of a tugboat changes from 2 meters per second to 4 meters per second in the opposite direction while a force is applied to a tugboat for 20 seconds. Complete the work and energy bar chart for this process. The bar heights should be correct in proportion to one another. So I'm going to let you chew on that by yourself for a moment, and then we'll discuss it. Figure it out. Help me out. So there are some people that have similar things to last time. Some people have more things. Talk me through your reasoning. Someone, not Jordan, she's talked too much today. Somebody else talk to me. I don't care who it is. David, back there, talk to me.
Alright, well, so the
Or you can call on somebody else.
yeah, I'm not exactly sure what I'm doing here, but what I initially thought was like, I don't know.
You can pass if you want. I don't mean that in a. I just.
Oh, yeah, okay.
I was just wanting to say, like, it can't be the same as the last one, even though, like, even if you, like, put -4 as the velocity and then square it, because it require more work to go the opposite direction. So that's why I thought it'd be, like, the distance from -2 to 4, so I changed it to 6 as, like, velocity.
Okay. It can't be the same because it's going the other direction. That's what you said, right? Others, do you agree? So what did you have? You had how many here?
For which one? What do you want?
For the kinetic energy, how much did you have?
18.
18. And then you had, so 16 there?
Yeah, but it seems a little high. I don't know.
So was it kind of arbitrary, or was it like a reason, like did you make that decision on purpose? Of 18.
Yeah, I used, like, the equation, but substituted in that velocity was 6, because you'd have to overcome the 2 going to the right, and then the 4. I don't know.
Okay.
Yeah.
Okay. Other people? Chris?
You said that it was the same as the other one,
Why?
since if you substitute -4 into the 1/2 mv squared, it just equals 16 again because it's squared.
Okay.
So it wouldn't change, it would just be the same as the other one.
Okay.
Direction.
Other thoughts? Does So 1 vote for the same, 1 vote for different. 18, because it can't be the same. So it just doesn't make sense for it to be the same, right? Because we've been so darn programmed that if we're going one direction, we turn around and go the other direction. That by golly, it must be different, right? But energy is or is not a vector. Is not a vector. It's a scalar. We just want to know how much. So here, the force that's causing this to turn or to go this way is just pushing in that direction, right? And remember that this isn't that we're not just marking the force. It's going to take a different force. I would agree. But all we're talking about is a change in energy. Work is just a change in energy. So we look at the energy before, we look at the energy after. The energy before is 2 blocks, which equals 1/2 m times 2 squared, right? The energy after is 1/2 m times 4 squared. So it should be how many blocks? Justin's excited because it should be how many blocks? It should be 8 blocks. Yes. Yeah.
Okay, I had a question. When
Yeah.
we were talking about like, the definition of work, though, we said that it was a force applied over a distance.
Yes. I agree.
So,
We have nothing in here that says anything about distance.
That's what I was thinking.
Work also equals the change in energy.
What's that?
Work also equals the change in energy.
Work is the change in energy. It is a force applied over a distance, right? So it's not instantaneous. So the force here is going in which direction? This way, right? This is the negative direction or something. Yeah, it's going this way. That's all well and good. We don't know how far it goes. All we know is a snapshot here, it's going 2 meters per second. A snapshot here, it's going 4 back this way.
but, like, if the forces are different between the first one and the second one, then how is their work? Does that just mean that their distance?
Because the distances would be different too. Yeah,
Okay.
yeah.
So the distances will somehow make it so.
I mean, we could do the math. I mean, let's talk about how we could do the math. Let's not do it just because I'm looking at the clock. Is that okay? If we could figure out if we have an initial velocity of 2 and a final velocity of 4 and a time of 20 seconds, we could figure out how far it goes, right? And you could do it for the other one too. And I'm guessing the distances wouldn't be the same.
Yeah, so the distances and the forces would somehow like make it so that it's
Right, so a big force over a little distance or a little force over a big distance.
okay.
Yes. Is that okay? It's a good question. It's not intuitive. Especially because we programmed ourselves to really care about directions, right? Directions don't matter anymore. That's a little bit weird in this stuff. Okay.